Right, so lecture number 28. So let us summarize the complete algorithm of the simplified marker and cell algorithm, the method, which is a semi-explicit method. So first we have to initialize, because we are using a transient approach where given the values of velocities and pressures at the previous time step, you calculate un plus 1, vn plus 1 and pn plus 1. So we need some starting point. So we start with u0, v0 and p0. We need these, otherwise we cannot proceed. So that is at n equal to 0. So the n value is 0 to start with. So you initialize these things. So once we have an initial guess or initial values for these, I won't say guess because they're actual values at the starting. So that's u0, v0 and p0. Then we start with our predictor corrector steps. So first is predictor. So we predict u stars and v stars. So the next step, step number 1, what we do is we predict u stars and v stars for interior points. This time we have to be clear about interior and boundary points. So we predict these using the governing differential equation, because governing differential equation is typically applied for interior points, because we already have boundary conditions for the boundary points. We'll use that for the boundaries. So first we apply this, and this is explicit method. So what happens is that you get u stars and v stars for all interior points. They're not dependent on other values because it's explicit approach. So next is because we still haven't touched the boundaries for u stars and v stars, because we need the boundary values also for u stars and v stars, because they are needed for as we'll see later that we will need that for updating the values of un plus 1 on the boundaries. So we need the boundary values also, u stars and v stars on the boundaries. So now we'll apply boundary condition. And fictitious points. So what I mean by fictitious points is, if you may remember that to apply higher order boundary conditions, we have to take into consideration some points outside the boundary. Okay, so the same idea. If you have those points, if you're trying to apply a higher order boundary condition, then you may have fictitious points. So you will apply this on the fictitious points too. But usually we consider that as a part of boundary. So we'll call it boundary points and fictitious points if they are existing. So once we have applied, so for example, u star on the top boundary, because the top boundary is no slip for backward facing step, for example. So in that case, u is 0 always. So u star is also 0 always. For the inlet, u is a parabolic profile, right? So u star will also be parabolic profile. And what we are doing in this case is that we are predicting it correctly. So u prime will be 0 for the inlet, and that is what we used, right? So we used u prime equal to 0 at inlet to get a boundary condition for p prime. Okay, so we already know how to apply these conditions, so we'll apply them at the boundary. On the outlet, we typically apply the fully developed condition. So del by del x of u star is equal to 0. So we can apply that because we already know the interior values So if you are applying first order boundary condition, so you can say that u star at the boundary minus u star at the interior point divided by delta x equal to 0. Okay, so now after these two steps, we have the u star and v star values on all the points including interior and boundary. So next is where the predictor step starts. Sorry, corrector step starts. Sorry. So for the corrector step, the first thing we need is we need the value of del dot u star, because that's going to be the right hand side of your equation. So we discretized that in the last lecture. So whatever that comes out to be, we evaluate that. We simply have to compute that term. So we'll say determine del dot u star. For all interior points. Okay, because we are solving the governing differential equation on the interior points, we'll have separate boundary conditions for p prime as we discussed yesterday. So we are solving the character equation for the interior point. So we need del dot u star for the interior points. Okay, so this equation, the discretization for which we discussed yesterday, we'll iterate that using the Gauss-Seidel successive over relaxation method. So that will help us solve this for all p prime values. But since you were using an iterative method where the values of a p prime is dependent on the boundaries, so it may happen that for some cells you may need the values of p prime, they depend on the neighboring points. Right? So it may happen that for some interior points which are near the boundary, you may need boundary conditions as well. So we have to solve this in conjunction with the boundary conditions. We cannot solve them separately. It's not an explicit method anymore. We are using an iterative method, so it includes points from nearby as well. So we need. So we'll say that iterate this for interior points, because we are solving this p prime using this equation for interior points. But we are solving it with the boundary conditions as well. Until convergence. What that means is that the residual should be small enough, less than some tolerance, epsilon tolerance, so that we know that we have actually found out the correct solution of the linear equations. Any questions till this step? So now that we have solved this elliptic equation for p prime for all the interior points, now we have p prime available on the interior points now. And actually we've solved it on the interior points, but we know p prime on the boundary points as well. because we have solved it with the boundary points, right? So we know the value of p prime on the boundary points as well. So I should actually say iterate this. So this equation is for interior points and with the boundary conditions. So we have p prime available on both interior and boundary conditions. So for example, you had del p prime by del x equal to 0 on the inlet. Right. So you are solving it with these equations. So for the boundaries, when you are writing the loops for the Gauss-Seidel SOR method, then you will be including the boundary points as well, updating the boundary points as well as we go on in the iterations. Right. So we have p prime available on the interior and boundary points now. So next is to get un plus 1, vn plus 1 and pn plus 1. That's what we do with pressure correction. So the velocity at the next time step now can be found out by adding the velocity correction to the predicted velocities. And this we'll do for interior points. The reason is that we'll have boundary conditions for un plus 1, vn plus 1 and possibly pn plus 1 as well. So we'll apply those boundary conditions for the boundary points. So let's discuss a couple of boundary conditions. So the boundary condition for un plus 1 on the walls will be 0. It's a no slip wall. All the walls are no slip. So u and v are always 0 on the walls. So what that means is that un plus 1 will also be 0. Vn plus 1 will also be 0. So rather than adding predicted velocity and u prime, let's straight away apply the boundary condition for un plus 1 and vn plus 1. Similarly for the inlet, for example, the boundary condition will be un plus 1 is a parabolic profile and vn plus 1 is 0. For the outlet, we are applying a fully developed condition. So we are saying that del by del x of un plus 1 is equal to 0. So if you are applying a first order backward difference, so what that will mean is that un plus 1 on the boundary minus un plus 1 on the interior divided by delta x is 0. You already have un plus 1 on the interior now from the previous step. So you can find the un plus 1 on the boundary. So after this, we have un plus 1 and vn plus 1 on the boundary points as well. Now what about pn plus 1? What are the boundary conditions for pn plus 1? We have talked about the boundary conditions for p prime. We still haven't talked about the boundary conditions for pressure. But we need pn plus 1 because when you go to the next step, predictor step, in a predictor step, the way it works is that you use the pressure from the previous time step, Pn. Right? So we need this Pn plus 1 which becomes Pn for the next time step. Okay, so we need Pn plus 1 on the boundaries. So what sort of boundary conditions should we apply on the boundary points for Pn plus 1?
These are the boundaries.
Right, so right now what I'll propose is that we'll apply the same boundary condition for Pn plus 1, for example, for the Neumann condition that we had for P prime. And I'll discuss why we are doing this. Okay. So I'll just write on the right hand side. So what that will mean is that del P by del N at the n plus 1th time is equal to 0 on inlet and walls wherever the velocity was directly del P by, so N will become depending on whether you have a wall which aligns with the x direction or y direction. For the x direction aligned wall, you will have, for horizontal walls, you will have del P by del y. For vertical walls or inlet, you will have del P by del x. So that's the same as what we had for P prime. And for the outlet, so P at n plus 1 at the outlet will be P infinity. That is what we propose, right? We propose that the outlet pressure is P infinity. So from there we got P prime is equal to 0 at the outlet. So P n plus 1 is P infinity. We'll ensure that it's always P infinity. So after this step, now we have the values for pressures also at the next time step, because we'll need these pressures in the predictor equation for the next time step. This predictor equation requires pressure at the boundaries as well. Some interior points will need neighboring pressures. That's it. So now with this algorithm, you can write a code yourself. It's always good to first have an algorithm so that you can use that to step by step write your code as separate chunks or modules. So now we'll say n equals n plus 1. So basically you move to the next time step, and then so whatever values were there in the previous time step, they all become the nth time step value, and you evaluate u and v and p n plus 1 by proceeding for this in this whole algorithm again. So this is the end of corrector step. This was, let's say, A. So we'll say that we go back to A. Or stop. So depending on how long you want to compute the solutions. If you want a transient solution, you may know when you want to stop. If you want a steady state solution, then the stopping criteria will be specified. That is that the difference, RMS difference between the values for u, v or p, whichever you want to use, is less than some epsilon steady state, then you'll stop. So if the values of velocities or pressure stop changing with time steps, that means you have reached a steady state. There's no more further change, so you can stop. But typically you cannot say it's 0, you say it's smaller than a small number. So for checking for steady state, we also have, in fact, that was given as an exercise in the lab for backward facing step. So I was just running it for certain number of time steps. So I told you to implement a stopping criteria where you say that the difference is less than some epsilon. Well, RMS difference. Up. Any questions? Some things to note, some notes. So as discussed just now, we can use this algorithm for solving steady state problems using false transients. I mean, the same method that we are doing, but we keep doing it until we reach a steady state, or we can solve an unsteady, real unsteady problem, whatever you want. That depends on the requirement of the your requirement or the customer's requirement, so to say. So in when using the false transient method for steady state, uh, the initial conditions do not matter, because whatever initial conditions you start with, you will reach at steady state. You can start with u equal to 0, v equal to 0, for example. So it's important to write these things. So let me write that. I should say the choice of IC, not the IC. I mean, you need the initial conditions, of course. Right? So you can choose any initial conditions as you want, but if you choose your initial conditions smartly, in the sense that the initial conditions are closer to the final solution, then your code will converge faster. You will need lesser number of these false transient time steps to reach that steady state. That makes sense, right? Because you are approaching that solution. If you start with something which is closer, you will need lesser number of time steps. So typically what happens is, for example, in a backward facing step, you have an inlet profile which is parabolic. So you know that once the flow starts, there will be flow velocities everywhere. Now somewhere the flow velocities will be less than the inlet, somewhere maybe larger than inlet depending on the cross section area. But typically it will be around inlet, not around 0. So if you start with a 0, it will need larger number of time steps to solve it, to reach that steady state. But if you start with the velocity on everywhere equal to u equals some u naught, where u naught is the average velocity at the inlet. So then what will happen is things will converge faster. Okay. So let's talk about the unsteady problem now. So initial conditions have to be realistic. It's like, you know, you do an experiment. if you're doing an experiment, you should know what your initial values of velocities should be, so that you can um, correctly find out what will be the velocity after some time later. So if you're starting your system with u equal to 0, v equal to 0, so you start with that. Now the question is, we also have a pressure, right? So we also need a pressure at time step 0. So velocity is typically you will know, but pressures, you may not know what the pressure distribution is at t equal to 0 for a given system or set of velocities, because and that can be found out because the indirect specification of correct pressure is that the velocities should satisfy continuity equation. So if you are initializing velocities as some values based on what you have an intuition for, or what your experiments have shown you, or what you are proposing, that initial velocity u0 v0 should satisfy continuity. So so what you do is you have to enforce a continuity equation on those initial velocities so that you find p0, because you may end up proposing a p0 which may not be the correct p0, in the sense that it results in your velocity your velocity field that you're proposing may not satisfy continuity, right? So we have to ensure that these velocity fields satisfy continuity. So that's important. So typically what we do is, just to be sure that we are providing initial velocities which are satisfying continuity, you actually use your algorithm once. So whenever what you are proposing u0 v0, you call it u star 0 and v star 0, and then you correct them using a corrector step. So you run the corrector step once with these u star 0 and v star 0. Whatever you are proposing, for example, you propose the initial conditions to me, I'll take them as predicted values and then correct them, because corrector step what typically does is it enforces continuity, right? That is what the corrector step was doing. So it corrects your estimate or initial guess for velocities by enforcing. So it will add a u prime and v prime to these u star and v star initial values, and that will ensure continuity is satisfied. Okay. So these are the true initial conditions now, which you have obtained from solving the corrector step once. So what about pressure? Now let's briefly go back to the algorithm where we applied, while applying the boundary conditions for Pn plus 1, we use the same boundary condition for P prime at the Dirichlet specified velocities, that is inlet and walls. Now what exactly is this? This is del by del n of, let's write it for the inlet. Let's use a different color. So the inlet we are saying del p by del x at n plus 1 is equal to 0. That's what we are applying in the algorithm. So what that basically means is we are saying that del by del x of Pn plus del by del x of P prime is equal to 0. So this is 0, we know that. This is what we got from the used velocity boundary conditions. But how can we say that del Pn by del x is also 0? So this is where our pressure at the initial step comes into the picture. You choose a pressure at t equal to 0, n equal to 0, so that del p by del x is equal to 0 for that initial pressure. So the easiest thing is you choose p 0 equal to 0. So we start with an arbitrary pressure P0 as long as it satisfies those boundary conditions. Because if P0 equal to 0 and so that means del P0 by del x will also be equal to 0, and del P prime by del x is always 0 on the boundaries. So this will ensure that del P1 by del x will also be 0 on the boundaries. And similarly, on the boundaries, del by del x of Pn plus 1 will also be 0. Okay. So we start with an arbitrary pressure as long as it satisfies these boundary conditions, and then we update Pn plus 1 as Pn plus P prime. But you may ask that why are we not using actual boundary conditions for pressure? There are some actual boundary conditions of pressure. For example, if I write, so I'll just note here that this, but not actual boundary condition for pressure on boundaries, of course. So what is an actual boundary condition for pressure? So if we write the Navier-Stokes equation for, let's say, for the inlet, we write it for the u velocity. So from there we'll get del p by del x will be minus rho times this quantity So I've written the Navier-Stokes equation for the x velocity and then moved the del p by del x on the left hand side. So this will help me find the pressure gradient on the boundaries. So I'm applying this for the boundaries. But the problem here is, just a second, the problem here is that to get your, I mean, let's say it was a wall, let's say if it was applied for a wall, then we'll have this del p by del x equal to rho times, so that's mu, so rho times nu, that is mu times del square u. Okay, So u is 0 at the boundary, at the wall, but del u by del x may not be 0 and its other derivatives. So this is what we have. So to get this pressure, you need velocities, right? And because to apply the boundary condition for pressure, you need velocities. And for solving the velocities, you need pressure. So you're stuck in a loop. A general hand wavy idea of why we don't apply the true boundary conditions for pressure. We just specify some arbitrary pressure field as long as our continuity is satisfied. So we'll start with something which is not correct, but continuity is specified, satisfied. So as we proceed, we may not get the actual pressure field. If you were to do an experiment, you may not measure the exact pressure. But our continuity is satisfied, so we are happy. Somebody had.
So this pressure from walls boundary condition.
Yeah. So if walls are not specified correctly, interior will also not be specified in the later time steps. Because a wall, you're solving electric equations for pressure. So if the walls are not correct, boundary conditions have a strong effect on the interior values. Typically in a problem, when you solve something, you specify boundary values only. You specify inlet velocities, right? And then everything changes by changing the inlet values. So the discussion is for the boundary, but that affects pressure everywhere. Some people call this pressure obtained from the SMAC method as a pseudo pressure. So I'll just write that this results in a loop. So pressure depends on velocity and velocity depends on pressure. So it's a vicious circle. Now this will start making a lot of sense when you actually discuss other methods where the pressure that you obtain is more realistic. It may seem quite overwhelming right now, but it's important to have this discussion because this will be important for you if you start using these methods for your research, for example, particularly. Just have one more thing. Can I take 2 or 3 more minutes? Let's finish it off. Now there are situations where, another note, so there are situations where the flow is unsteady. So in that case, a fully developed condition cannot be applied because things are changing with time. It's like if you put a probe and you measure the velocity at the outlet, you will see a sinusoidal. It could not be, it could be anything. But the thing is, it's changing with time. So it's unsteady, right? So if it's unsteady, I cannot just say that the velocity at this point minus velocity at this point is equal divided by delta x is 0, because that is not the correct boundary condition. So the correct boundary condition for unsteady flow at the outlet is it's actually called an outflow boundary condition. For unsteady flow. So situations suggest when you have turbulent flow. So by nature, turbulence is unsteady. So we apply this boundary condition. We actually say the material derivative of phi. So del phi by del t plus some u average over the cross section, some area average, for example, del phi by del x or del phi by del n, where n is the outward normal. This is equal to 0. Now remember, this method was an explicit method. And explicit methods have an issue with stability. We learned till now, right? So we need some sort of a specification for time step size for this explicit scheme. We saw earlier that when your numerical Fourier number has to be, for explicit schemes, numerical Fourier number has to be less than half. Otherwise, the scheme becomes unstable. The errors will grow with time. Similarly, for upwind schemes, for explicit methods, we'll need your Courant number to be less than 1. So all these conditions resulted in some constraint for the time step size, delta t. Given a constant delta x in a problem, your delta t will have to be specified. It will have to be less than something. That's what we saw, that if for explicit schemes the delta t becomes so small sometimes that it becomes prohibitively expensive, or it takes a very long time to reach that time step, time in the problem. Right? So delta t will have to be specified for this explicit scheme. So we have different heuristic criteria for specifying delta t, because here we have both diffusive terms as well as convective terms. So what do we use? Do we use a Fourier number like gamma less than half condition here, or should we use CFL less than 1 condition here? Or we can maybe combine both of them together. So just summarize that. So one way to specify that, we have different time scales. So one is diffusion scale. So if you were to use diffusion stability, that will give us the diffusivity nu here instead of alpha. So this was the condition. So from here we can get delta t, we call it diffusion time step, has to be less than equal to or if you use the convective time step, so we call it the convective stability. Or so which one should we use? Or we can choose the smaller of that. So you can just simply say that delta t that you're choosing has to be less than equal to the minimum of this delta t diffusion and delta t convection. In some cases you will see that we'll combine the two and create just one delta t, which is smaller than both of these. So in both of these you have 1 upon something, so that's something that you have, you just increase the denominator by adding the denominators of both. So for the first case, in the denominator we had 2 nu times this, so we just use that, but I add the denominator of the convective time scale as well, so that is and you can check that of course this quantity is lesser than both delta t diffusion and delta t convection. And remember that u and v are changing with space. They are not the same everywhere. So what that means is you're not, where are you checking this? So you check for every point in the interior. Because you and me are different, right? So you check for every point, and wherever you find the worst case scenario, wherever your delta t comes out to, because delta t cannot be different for different spatial points. It has to be the same. So you find out this for all interior points and you find the minimum of that. If at some point your u values are let's say very large, so that will result in a very small delta time there on overall. So it's called the worst case scenario. So you have to show that the delta t has to be smaller than this, because the CFL number or the combined effect has to be less than equal to something at all points. Okay. So this brings us to the end of our discussion on semi-explicit methods. We discussed in a bit of a detail. In the next class we have a quiz. We just have a quiz on that day, and then you can relax. And the next week we'll start with our implicit. So we'll discuss just one implicit method, and then we'll end the course. We'll start our discussion on implicit methods starting next week, and we'll also have a demo on OpenFOAM and some other finite element software. So we have some time now. We have actually been we are going on track, but we have been comfortably able to finish things on time. So we'll take it easy towards the last few weeks. I'll summarize things and also give you a demo of different open source codes.